Welcome back to the fifth and final lecture about multivariate twin modeling. So, just to recap, section 1 was about going from the univariate model to the bivariate model, and then from the bivariate to the multivariate. Dirk Pelt discussed the independent pathway model, a multivariate model based on the common factor model. That was a slideshow 3 and 4, section 3 and 4, and this last lecture is about the common pathway model. Here's a slide with our notation. You've already seen this. It's just an overview. We thought it might be handy. Okay, Dirk Pelt presented these results. This is the results of the independent pathway model as applied to the skinfold data. And this is the upshot of that model. Yeah, so it's a model with three common factors, three common variables, common in the sense that they're common to all four phenotypes, AC, the C stands for common, AD and EC. In addition to the common influences, you can see there are phenotype-specific influences, E, A, but no D, because that was Dirk's upshot of his testing. He found that there was no phenotype-specific dominance influences. Okay, that was the independent pathway model, and in this slideshow we're going to go from the independent pathway model to the so-called common pathway model. And the common pathway model is also known as the psychometric model, and the interpretation and the justification of this model is based on the psychometric theory of the common factor model. So we're going to first return, believe it or not, we're going to return to the univariate model briefly to make a certain point. In addition, we're going to change the phenotype from skinfold data to a measure of neuroticism, measured using a very small test, just a test comprising 4 items with 5-point scales. So that'd be something like, I worry a lot, and then the answer options are, does not apply to me at all, option 1, 2, applies to me very much, response option 5. 4 of these items. Okay, so here are the summary statistics in a sample of monozygotic and dizygotic twins for the sum score on this neuroticism test. Yeah, so the sum score is nothing other than adding up the 4 individual scores of each person, and that gives you the persons, that twins, neuroticism sum score. Okay, in the blue you can see the summary statistics. The MZ sample comprises 1528, the DZ sample comprises 1277 twin pairs. You can see the means, standard deviations, not very important stuff. And then you can see the covariance matrix of the MZs and the DZs, and in parentheses the correlations. And based on the correlations, just visually inspecting the correlations, you can see it's at 0.18 in the DZs and 0.38 in the MZs. Okay, so we're going to start with analyzing, fitting a twin model to these data. Okay, my point of departure is the ADE model because 2 times the DZ correlation is larger than, just about larger than the MZ correlation. So I'm going to start with the ADE model as shown in the path diagrams. I'm going to test the D. As it turns out, I can drop the D. So as an aside, I'm testing the D in the variance components model, but the path diagrams you can see are path coefficient models. Yeah, so there's a distinction. And we invariably use the variance components models to fit variance components, but you can use the coefficients representation to represent the model visually. Okay, the test of the variance of dominance was not significant, so I conclude that there's no dominance, provisionally at least. So, and the results of the AE model are shown in numbers at the top of the slide, but also in the path diagram. So on the left, you can see the raw variance, the raw path coefficients, and on the right, you can see the standardized path coefficients. And at the bottom of the slide, the standardization. So if you wonder If somewhere along the way you've forgotten how this standardization will work, stop the PowerPoint and do the sum at the bottom of the slide. Okay, but we end up with the result summarized here. What we have, just to be clear about what we've done, what we have is a proxy for the latent variable neuroticism. I haven't observed neuroticism directly because I cannot, it's a latent variable. But I can observe the sum score on the test comprising 4 items that was meant to measure neuroticism. Okay, it's that sum score that I subject to my twin modeling, and the results are shown here. What is the narrow sense heritability of the neuroticism score, of the scores on the neuroticism test? 37.8. 37.8% of the variance is due to individual differences in A. Okay, this is a statement about the proxy. This is what we get. But what do we actually want? In an ideal world, we'd be able to measure the latent variable directly, and then we could carry out the analysis of the latent variable directly, and that would give us what we actually want, and that is a statement about the latent variable. Okay, so it's important to realize generally in psychology and in other fields that the test you have administered gives you test results, test scores, but these test scores generally are a proxy for something that you cannot observe directly, namely in this case neuroticism. Okay, so just a brief psychometric background, because it's important to the common pathway model. How do we know that the neuroticism sum score is a proxy for the latent variable? Now, the answer to that is simple and has to do with the validity of the test. The items 1 to 4, N1 to N4, were designed to measure neuroticism, designed by psychologists who know all about the latent variable neuroticism. They know what it is, and they know how it manifests behaviorally. And based on that knowledge, they constructed the test with these 4 items. So that's theory. Now, that's the basis for the validity of the test. On the empirical side, we can take a look at the correlations amongst the item test scores. Yeah, so we're talking about the item scores on the test. If the theory is correct that these 4 items measure the latent variable, that means that they are all influenced, dependent upon the latent variable, and that implies that they should correlate. Yeah, if each and every item measures the latent variable is a common influence to all 4 items, and that means that the items should correlate because they're all dependent upon the latent variable, as shown in the figure bottom right. Yeah, so this is just a path diagram as we know them from the twin modeling. Yeah, the latent variable neuroticism predicts or directly and causally influences the item scores. So the item scores are directly and causally dependent upon the latent variable, and if that is so, then we can use factor analysis to estimate the regression coefficients of the items on the latent variable, which in this context are called factor loadings. Yeah, so I've done this actually. I've taken the correlation matrix as shown here, and I've used a R program to carry out to fit the single factor model. And the results you see are given in the path diagram. So item 1 is correlated about 0.69, about 0.70 with the latent variable, and the residual, the 0.516 shown in red, that is the variance in the first item that is not explained by the latent variable. Yeah. Okay, so what we did was we carried out the analysis of the sum scores. We get the results as shown top left, and this is a statement about the sum score, which is supposed to be a proxy for the latent variable. Now the question is, how will the results based on the proxy reflect the variance components associated with the latent variable? And the answer is possibly not so well. And I'm going to illustrate that later on. I'm going to show you what exactly not so well means in this context. Why not? Well, for one reason, the sum score is just a proxy. It's not the latent variable itself. It is an approximation. There's going to be some approximation error. And also the items N1 to N4, the observed variables, they include measurement error. So if you recognize that n1 to n4 include a measurement error, then you have to recognize that the sum of n1 to n4 will also include measurement error. And that is going to have a bearing on the results. How exactly, we'll see later on. There's a reference on this slide shown at the bottom, and that is a reference to this discussion and other aspects of using sum scores. Okay, so what are we going to do about this? What is the solution to the problem that the proxy is not the latent variable? Well, one thing we can do, and this is the subject of the common pathway model, that is, we can combine the common factor model, yes, bottom left, and the twin model, top left, into a single model. And this is, as shown, the path diagram on the right, this is the common pathway model. And what it does is it combines the ADE or the ACE variance decomposition of the latent variable and the common factor model. And we can get at the latent variable, or we can get at the variance decomposition of the latent variable because we're including the common factor model. We're relating the items n1 to n4 to neuroticism, and then we can carry out the decomposition. So this is the common pathway. It's also, as I mentioned earlier, it's also known as a psychometric model because it incorporates the common factor model to link the indicators, that's the observed variable n1 to n4, to the latent phenotype neuroticism. Yeah. That's why it's called the common factor model. And the common factor model is based on the psychometric model, that is the factor model, and the factor model is actually a measurement model because it relates items to the latent variable. The common pathway model is also a mediation model because the effects of ADE on neuroticism are clear, direct effects, but ADE also have an effect on the items via neuroticism. That means that neuroticism is the mediator. It's mediating the effect of A, D, and E on the items N1 in the path diagram. Okay, so what is the effect? How do we quantify the effect of A on neuroticism? Well, that's quantified by the parameter A or by the variance of A, sigma A squared. What is the effect of A on N1? Well, if you take the path coefficient model, then it's A times F1. And that's an important result we're going to need later on. So what is the effect of D on N1? That's going to equal, in the path coefficient representation, D times F1. What's the effect of E? E times F1. Yeah, what's the effect of A? As shown in the slide in bold, A times F1. Remember that because we're going to need it. This model implies a decomposition of variance at two levels. Item level, considering item N1 here, and the latent variable neuroticism. So the decomposition of neuroticism simply into three components. So if you're using a path coefficient representation, the decomposition is A squared plus D squared plus E squared. That's shown at the top on the left hand side. And then under that you can see the decomposition of the item score variance. If you just consider the factor model here, regressing N1 on neuroticism, the latent variable, then the decomposition is F1 times the variance of neuroticism times F1 plus the residual variance shown at the bottom of the path diagram, sigma epsilon 1 squared. So we know that the variance of neuroticism is decomposed into A squared, D squared plus E squared. So we can write the decomposition of variance of the first item as F1 squared times the brackets. This is the second equation in the middle. F1 squared times the brackets, A squared plus D squared plus E squared plus the residual. We can represent that in path diagram, in path coefficients or in variance components. And at the bottom you can see what the actual, and based on the above, based on the bit in the middle, you can see what the decomposition is of the item N1. It's into an A part, a D part, and an E part, and then a residual. And the residual in this context, in the context of the common factor model, the residual would be interpreted as measurement error. So anything that's not explained by the latent variable in the common factor model is called measurement error. Let's consider the residuals, that's the epsilons in the figure on the left, just for a second longer. In the independent pathway model, if you remember Dirk's second PowerPoint presentation, he decomposed the residuals into A, E, and possibly D components. Yeah, that's the figure shown on the right. Yeah, so there appears to be a difference between these two models with respect to the residuals. In the independent pathway model, we're saying they could include A, D, or C components. In the figure on the right, we're calling the residuals error variances, and that's it. But that's not completely true, because if we want, we can include in the common pathway model the decomposition of the residuals. So what we can do is we can actually subject the residuals, the epsilons in measurement errors, so-called in the previous slide, we can subject those to their own ADE variance decomposition, as we do or have done in the independent pathway model. So this slide shows you the full twin model with item-specific ADE decomposition, but only shown for the first item, just to avoid clutter. You'd include this decomposition, obviously, for item 2 to 4 also. So this is the model including ADE for the residuals. We can fit this model using different parameterizations. The parameterization on the left is the path coefficients parameterization, where the A, D, and E are standardized. So you're estimating A, D, and E path coefficients. It's important to realize that the A squared, D squared, and E squared have to add up to 1. So that's a constraint that you'd impose if you're fitting the model using the path coefficient parameterization. If you are interested in testing variance components, then invariably you'd use the model shown on the right, that is the variance components parameterization. So there you can see the 1 asterisk, that's a fixed values of 1, and then we're estimating the variance of A, D, and E at the top, sigma A squared, sigma D squared, sigma E squared, and at the bottom we have 4 factor loadings. And to identify the model, we'd have to fix the first one, or rather we have to fix 1 to equal 1. So one of these factor loads have to be fixed to equal 1, and I've chosen the first one, but that's arbitrary. You could also fix F4. Okay, so these two, in the way I like to do this is I like to fit the model using variance components, but to represent the model using path coefficients. But that's just my preference. Regardless of that, if you want to test variance components, if you want to test whether the D variance is 0 or not, then you'd have to use variance components parameterization. Now finally, in this figure, you can see at the bottom, I've resorted to the epsilon 1, 2, 3, 4 as residuals. Yeah, but that's, as you know from the previous slide, we could have replaced that with ADE or ACE decomposition. Okay, now there's the following 2 slides, or this slide is actually the most complex slide in the whole PowerPoint presentation. In fact, probably in all 5 on this subject. What I want to do is I want to explain to you how the common pathway model is nested under a special case of the independent pathway model. So what that means is that I can compare the common pathway model and the independent pathway model using a likelihood ratio test. I can fit the independent pathway model, the common pathway model, and then I can carry out a test whether the common pathway model fits the data as well as the independent pathway model. Yeah. So that means that the common pathway model is a special case of the independent pathway model. Yeah, that because it's a special case, the common pathway model is nested under the independent pathway model, and that allows us to conduct the likelihood ratio test, the comparison of the 2 models. Do they fit equally well? Okay, to explain this nesting, what we'll do is the following. So let's suppose that, yeah, the common pathway model is a true model. Okay, and we're not going to think about the residuals, the residual terms. That's not important. And we're just going to consider an AE model to keep this simple. Okay, so let's suppose that the true model is the common pathway model. Yeah, in that case, take a look at the table top left. In that case, the relationship between item 1 and the A is equal to A times F1. Yeah, and so the first row, the A times F1 and E times F1, those are the effects of A and E on item number 1. So it's from A to the latent variable, yeah, path coefficient A, and then from the latent variable to the item, path coefficient F1, and that gives us A times F1. And the same applies to E, and this applies to all 4 items. Yeah, so the red table on the left, red part, that is the true model. Okay. Now what we're going to do is we're going to fit, given that that is a true model, but we're going to fit the common pathway model. So I'm going to estimate A1, A2, A3, A4, E1, E2, E3, E4. These are the loadings or the coefficients in the regression of the 4 phenotypes on the common A and the common E in the independent pathway model. Okay. Now we're going to switch to the table on the right, and what I'm going to do is I'm going to consider the first item, so that's the result shown in the green box. Yeah. Now I know that the true relationship between item 1 and A equals A in red, A times F1. But what I'm estimating is A1 shown in blue, because I'm fitting the independent pathway model. Okay. So the green box, we have estimated A1 and we've estimated E1. But A1 is truly equal to red A times red F1, and E1 is truly equal to red E times red F1. Okay. Now if I take the ratio of A1 to E1, then you can see, this is the table top right, second column, you can see that that is going to equal red A divided by red E. Okay, that's the basis of the constraint. This is a proportionality aspect of A1, blue A1 divided by E1 gives us red A divided by red E. Okay, A1, E1, independent pathway model parameters, red A, red E, common pathway model parameters. Okay, and the same applies to A2, A3, and A4. So all 4 items will display this proportionality constraint. So if I take the A4, blue A4 of item 4 and divide it by the blue E4 of item 4, then it's going to give me the same ratio, red A divided by red E. Okay? Okay, so this implies the following. I can fit the independent pathway model, and I would estimate A1 to A4 shown in blue, E1 to E4 shown in blue. But if I estimate A1 to A4 and E1 to E4 subject to the proportionality constraint shown at the bottom of the slide, then effectively I'm fitting the common pathway model. So what are these constraints? Well, what I'm going to do is this. I'm going to estimate A1 and E1, 3 parameters. And then in my OpenMX script, I'm going to calculate the ratio of A to E. Yeah. At this point, I know that A2 divided by E2 should equal that same A divided by E. Yeah. So that means that I know that A1 divided by E1 should equal A2 divided by E2. That's shown at the bottom of the slide on the left under proportionality in purple. Okay, from the first proportionality constraint, A1 divided by E1 equals A2 divided by E2, shown in blue. That implies that I can solve for A2. A2, I don't have to estimate it. I estimate A1, E1. A2 can be derived from A1 divided by E1 times E2. Okay, so that is pretty complicated. What I'm doing is this. I'm estimating A1 to A4, E1 to E4, shown in blue in the independent pathway model. However, if I estimate A1 and E1, E2, E3, and E4, then I can derive from the proportionality constraints shown in table top right, I can derive the values for A2, A3, and E4. Okay, so that is the nature, the background to the nesting. So I estimate 8 parameters in the independent pathway model, yeah, or I impose my constraints. In that case, I estimate 5 parameters, A1 and then E1, E2, E3, and E4. So the difference in the number of parameters is 3, and that is the number of degrees of freedom of the likelihood ratio test. Okay, so the take-home message is common pathway model is nested under the independent pathway model. Okay, here's just a numerical example illustrating this. Yeah, so you could stop this PowerPoint here, get your paper and pencil, or pencil and the back of an envelope, and do the sums, and you can see that the proportionality constraints hold, and that you can derive the A2, A3, and A4 parameters based on the proportionality constraints. So because they're nested, again, we can carry out a likelihood ratio test. And this is just showing you the two models that for the ADE decomposition of 4 items. The independent pathway model, this is using variance components parameterization. On the left, the common pathway model. On the right, the independent pathway model. And these two models are nested due to this proportionality constraint, which I discussed with respect to A and E, but you can also discuss it with respect to D and E, yeah, and derive similar constraints based on the proportionality constraints. So let's illustrate this. What you see here are the summary statistics, the correlation matrices of MZs at the top, DZs at the bottom. Sample size is shown at the top, 1528 and 1277. So quite large samples. Shown in red are the cross-twin within item correlations. And you can see that the MZ correlations are all larger than the DZ correlations. And shown in green are the cross-twin cross-phenotype correlations. And based on those, you can see that the MZ cross-trait, cross-twin correlations are all higher than the DZ correlations. And that suggests that the red results in red suggest there are genetic influences on the item scores. And the green tells us that there are probably genetic influences contributing to the covariance among the item scores. Okay, so we're going to fit the common pathway model to these data. We've already seen this, so based on the items we can carry out the sum score analysis, but we've already seen those results. We'll return to those in a second. I'm going to start out with the ADE model. So here are the results in a table of fitting these models. The first model at the top row, model 1A, that's just unconstrained model, estimate the covariance matrix of the MZs and the DZs. The second model is estimate the sigma A, sigma D, and sigma E. These are 4x4 covariance matrices for the A, D, and E components. And I compare model 1A and model 2A and find that the model fits well. So the ADE decomposition is acceptable from the point of view of goodness of fit. Then based on the correlations, I know that there's probably not a big D component. So I drop the D component and ask, does that model fit? Do I need the D? And the answer is that's row number 3, model 2B. I don't need the D component, the sigma D. And the sigma D, this is a 10 degree of freedom test because sigma D, the dominance covariance matrix of the 4 items contains 10 items, 6 covariances and 4 variances. So I'm fixing those all to 0 in the variance components model, so the difference in the number of degrees of freedom is, difference in the number of parameters is 10 equals the degrees of freedom. Okay, the next model is the independent pathway model as fitted to the AE, using the AE model. So it's an AE independent pathway model, and I compare that model, 3A to 2B, and I find that that model fits perfectly well. So at this stage, I know the independent pathway model gives me a good representation, as good a representation as the model 2B. And the next step is fit the the common pathway model, that's 4A. And again, now just to see the nesting in action, I can compare 4A to 3A. And that's going to be a 3 DF test, yeah, as I explained 2 slides ago. And we find that the common pathway model fits adequately. So that means that I can go from unsaturated to the common pathway model, and I know that the model fits reasonably well. Yeah. So here are the results of the common pathway models, the standardized representation of the results. And you can study this for yourself, but what I want to point out specifically is, let's take a look at the decomposition of the latent variable neuroticism. Yeah, in the common pathway model, we can see that again, all these numbers are standardized, so the narrow sensory ability of neuroticism is 46.5. Yeah, if you compare that to the narrow sensory ability we obtained in the analysis of the neuroticism score, you can see the difference. Yeah, it's 46 versus about 37. Yeah, so that means that the results we get from the neuroticism sum score are not really representative of the results we get when we analyze the latent variable. And that's why this is an important distinction. This is a justification for considering the common pathway model. You can also take a look at the residuals, and if you take a look at the residuals, you can see that the A residuals, A1, A2, A3, and A4, very, very small, except maybe N2 residual, 0.145, and the E residuals are quite large, and that would be consistent with the E residuals largely representing error. Okay, 2 more slides, I think, and then this is finished. This shows you a generalization of this model, yeah? Because so far I've been talking about a single common factor model, common pathway model with one latent variable called neuroticism. But you can generalize that from one to many latent variables. On this slide you can see the common pathway model that links neuroticism to extroversion, each measured with 4 items, and this is just a common pathway model. Yeah, the items are predicted by neuroticism or by extroversion, and extroversion and neuroticism are possibly correlated. So this is a measurement model, a psychometric model, a common factor model. Yeah. Now you could take this model. If you've got twin, then you could expand. This is not a twin model. This is just the AD model shown for twin 1 members or twin 2 members. So this is the way you'd generalize the common pathway model from a single common factor model to 2 common factors. I think that concludes this PowerPoint. We'll be fitting the common pathway model in the practical, so you're going to get hands-on experience with this. Finally, here are some references in which this model has actually been used in the literature. The reference at the top is one of, I think that's an important paper because that launched the whole idea of common pathway model versus independent pathway modeling. There were other papers related, but that is the major reference. Thank you.